In this video, we are going to learn how to detect objects using blob analysis and annotate videos. Specifically, we will talk about how to convert between color spaces, perform color thresholding, how to perform morphological operations, detect objects using blob analysis, and insert text and shapes in video frames. This training will be useful for all AUVSI teams since it talks about performing general image processing and computer vision tasks such as thresholding, morphological operations, etc. Blob analysis will be specifically useful for teams that are interested in doing color-based object detection. We would also like to thank the Cedarville University RoboBot team for providing us with image and video files for us to use in this training. For example, let us take a scenario where green buoys are objects of interest to us. So we would like to find the object and mark it on the image or a video using shapes and texts. A common first step to do color-based object detection is color thresholding. Let's switch to MATLAB and see how we can do this. Let's open up a starter MATLAB script here called blob_start.m. This script has several comments that will help us build our algorithm in steps. Let's begin by loading a couple of sample frames. So to do this, I use the load commands and provide the mat file that has my sample frames here. And then let's go ahead and visualize this using our subplot command. And then using IMShow here on our video frame. In this case, it's called video frame 1. Let's go ahead and save this file as blob detection and go ahead and run this section here. So here is the image which has the green buoy, which is the object of interest to us. Next, we need to do color thresholding to isolate the green buoys. To perform color thresholding, let's use a built-in MATLAB app called Color Thresholder. To access this app, let's go back to MATLAB here. Go to the Apps tab here, click on the drop-down, scroll down to Image Processing and Computer Vision here, and then click on Color Thresholder here. Let's begin by loading an image to perform thresholding on. So click on the drop-down here for Load Image. Let's load image from a workspace here. Click on vidframe 1, which is the image we need to do thresholding on, and click OK. The app then asks which color space you would like to use for thresholding. The app allows us to look at some commonly used color spaces quickly and find out which one looks promising. The HSV color space is often used to select colors from a color wheel or a palette because it corresponds better to how people experience color than the RGB color space. Let's choose the HSV color space by clicking on this option here. The app opens an interface that has an image preview on the left and the controls to threshold the image on the right. The three controls correspond to the H, S, and V parameters of the image. Let's play with the H plane to isolate the green buoys. So I'm going to click and drag this arrow here to make sure the output only has the green part of our image. Having the hue limits show only green shows the green buoys and the tree line here. Let's adjust this control a little more to see if we can see only the green buoys and reduce the amount of tree line that is present in our image here. Now we can play with the saturation controls to isolate the buoy even more. Click on the Show Binary button to see a high contrast version of this image. Sometimes this is useful to fine-tune the thresholding since the image is high contrast. So let's go ahead and tune this here. Note that the tree line doesn't completely go away with the thresholding operation alone. We will need to perform more operations to get rid of it in subsequent steps. Once we are content with the thresholding result here, click on the Export Images button here to export the thresholded image. However, in a video with multiple frames, we need to perform thresholding using MATLAB code. To do this, click on the drop-down here and click on Export Function. MATLAB automatically generates a function that can be used to perform thresholding on any input image with the threshold limit that was obtained interactively in the app. So let's scroll down here. Here you can see the three channels corresponding to H, S, and V and their limits. Note that the automatically generated function also uses the RGB to HSV function. This is because we chose to work with the HSV color space, and this function is used to convert an image from the RGB color space to the HSV color space. Similar to this function, there are several other functions to convert between the different color spaces. Refer to the documentation to get more information about this. Now, let's copy the limits and calculations here into our script to perform thresholding there. So I'm going to go ahead and copy these commands here and use Ctrl+C, which is the shortcut for copying. Close this function here because we don't need this anymore. And then paste the thresholding commands here in the threshold image section. Let's visualize the output of the thresholding using subplots and then IMShow on BW, which is the thresholded image. Let's go back up and make sure the input to the RGB to HSV function is widthFrame1, which is the name of our input image. Let's clear our workspace, close our figures, and then run the script here. So here we see the original image and the thresholded image. We have successfully thresholded the example image to isolate the green buoys here. Let's go back to the presentation and do a recap. As a first step to do color-based object detection, we used the Color Thresholder app to load a sample image and converted it to a color space of our choice, in this case HSV. Then we used the H and S controls to isolate the green buoys. We also talked here about the Show Binary button, which helps us fine-tune our thresholding because the binary image is high contrast. Using the Export Function option, we found the limits used for the different channels, namely H, S, and V. Here we see the result of the thresholding. Notice how there is noise in the image. Thresholded binary images like this sometimes contain various distortions, such as the noise here. Blob analysis can remove most of these disturbances, but noise close to the area we would like to detect will still remain unaffected. We can remove these disturbances before performing blob analysis using morphological operations. Most morphological operations have a structuring element. We slide the structuring element over the image of interest to compare their pixel values. These elements can assume many different shapes, for example, rectangle, disk, diamond, etc. We can create a structural element using the strel function. We can see an example here of a line element of length 3 created. The second element of the strel function becomes the length parameter. The third argument is the degree, that is the counterclockwise angle of the line with respect to the horizontal axis. In this case, we have it as 0. So the structuring element here is a binary image that is 3 pixels long. Next, we slide this element over an input image to compute the resulting output image. Here, the green circle denotes the origin of the element, and the rest of the pixels are in the neighborhood. Now let's compare this to the first element of the image by lining up the origin with the first element of the input image. Based on this comparison, we could do several different types of morphological operations to obtain the output image. For example, we could simply compare the respective pixels and see if any of the input image pixels are high or 1 within the neighborhood. Then, the corresponding output image's origin location is also set to 1. This operation is called morphological dilation. Let's slide our structural element to the next pixel in the input image. We compare the first element 1 and an empty pixel, the second element 1 and a 0, and the third element 1 and a 1. So there is at least one high pixel value within the neighborhood, so we populate the output image with a 1 too. Similarly, if we slide again, we can see that there are no high pixels within the neighborhood of the input image, so we can set the output image to 0 as well. Like we discussed before, morphological operations could be of several different types, and we discussed only the dilation operation here. We can implement the dilation operation and several other morphological operations using the different functions in the image processing toolbox as listed here. Let's switch to MATLAB to see how to implement a morphological operation. In our script here, let's scroll down and begin by creating a structural element here. To do this, we use the strel function. This function takes in the shape as the first input. Choosing the correct structural element depends on your specific image, application, and morphological operation intended. Refer to the documentation for more information on how these structural elements work. For this particular example, let's go ahead and create a disk element. The second argument here refers to the radius of the disk in terms of the number of pixels. Let's set this to 3. Again, this is an experimental parameter tested for different sample images to see what would be the correct parameter for your image and application. Let's go ahead and end this function here and then set this to a MATLAB variable. In this case, I'm going to call it disk element. Next, for the morphological operator, we discussed the dilation operation before. The other fundamental operation is called erosion. Apart from these two fundamental operations, there are several compound operations. For example, an erosion followed by a dilation is called an opening. This operation can help open a gap between objects connected by a thin bridge of pixels. We can do this operation using the IMOpen function. So here I can say IMOpen of the first input is the image itself. So in this case, it's the thresholded image BW, followed by the structuring element. So in this case, that is disk element. The output of this function is also an image. So here I can set this to IBW open. Now let's go ahead and visualize this output. To do this, I'm going to copy the commands here and then paste it here, and then make sure that the subplot appears in 133, and then here the image is going to be IBW open. Let's clear our workspace and close all our figures and run this here. If we take a look at the images here, the third image here is the output of the morphological operation. We can see that the tree line has been removed and it is a relatively noise-free image. Now let's do blob analysis on this image. We will detect blobs of certain area because we can see that the green buoys correspond to bigger blobs. We will restrict the detection of blobs to area between 200 and 5000 pixels here. To do this, we will use the blob analysis system object. Let's go back to our script here. Let's set up the system object first. blob analysis equals vision dot blob analysis. Now let's set up the area properties. So first, let's set up the minimum blob area to a value of 200 pixels, and then the maximum blob area to a value of 5000 pixels. The values for these parameters are tuned by testing it on sample images. Similar to other system objects, we can use the properties and method functions to retrieve a list of properties and methods for this particular system object as well. To perform the actual blob analysis operation on the video frame, we need to use step on the blob analysis system object. So here I can say step on our blob analysis system object, followed by our input image. So in this case, that is IBW open, the output of our morphological operation. The blob analysis system object returns three outputs by default: the detected blob areas, the centroids of the detected areas, and a bounding box specification around the identified blobs. So let's set the output variables for this. So here I can say object area, comma, object centroid, comma, bounding box output. Let's go ahead and run this section here and go back to the command prompt here. Let's type out bounding box output here. So this is the output of the blob analysis. The bounding box output has the X and Y position of the blob, followed by the width and height of the blob. Now that we have identified the blobs, we need a way to visualize the results of the blob analysis. To do this, let's go ahead and annotate the original video frame with shapes and text. We can use the insert shape function along with the bounding box output of the blob analysis here to do this. Let's go back to the script here. So let's go ahead and use the insert shape function. The first argument is the image itself. So in this case, that is width frame 1, followed by the shape. And in this case, we are going to choose a rectangle, followed by the position, which is governed by our bounding box output variable, which is the output of the blob analysis. Apart from these arguments, the insert shape also has several other arguments that you could set. For example, I could set the line width property to 4 for a thicker rectangle to appear. Please refer to the documentation for more information on additional parameters and their values. The output of insert shape is an image with the inserted shape. So let's go ahead and set this to a variable called iShape. Note that the default color for the shape is yellow, which will look okay on our sample image, so we will leave it at the default value. Now let's go ahead and visualize this image. So to do this, let's open up a new figure. And I'm going to copy the subplot and IMShow commands here and paste it here. And then we are going to say subplot 1, 2, 1. And then IMShow of the shape inserted image here, which is iShape. Let's go ahead and run this section here. So here we can visualize the output of the blob analysis. We use the bounding box output from the blob analysis and fed it to the insert shape function to insert it into the image. Another way to visualize the blob analysis is to display the number of blobs detected in the video. We can do this by inserting texts. We can use the text inserter system object to do this. Let's go back to our script here. First, let's figure out the number of detected blobs by computing the number of areas returned by the blob analysis system object. So we can say number of objects equals number of elements in the object area output variable of the blob analysis. Then we need to set up the text inserter system object. So here we can say h text inserter equals vision dot text inserter The first input is going to be the data type of the text to be inserted. So in this case, we are going to insert integer, so it is %d here, followed by the location of the text to be inserted. We would like the text to be inserted near the top left of the image, not exactly at the top left corner, which is going to be 0, 0 coordinates. So let's set the pixel location to 2020. Then let's set the color of the inserted text to yellow to match the shape's color. So here we can say color followed by the RGB value of yellow. So it's going to be 255 for R, 255 for G, and 0 for blue. We can also set other parameters such as font size. In this case, the default font size is 12, which is small. So let's increase it to a higher value, let's say 30 here. Now, to apply the text inserter algorithm, we need to use step on this system object. So I can say step on our hTextInserter system object, followed by the image in which we want the text to be inserted in. So in this case, that's our shape inserted image, followed by the text to be inserted. In this case, that is the number of objects. Note that we specified the data type of the text to be inserted as integer here. Number of objects is a double variable, so let's go ahead and cast it to an integer here. The output of this step will be an image, so let's store it in a variable called iText. Finally, let's go ahead and visualize this output. To do this, I'm going to copy the subplot and IMShow commands here, and then paste it here. And then I'm going to say subplot 122, and then IMShow of iText here. Let's go ahead and run this section here and take a look at our output. So here we see the shape inserted image on the left and the shape and text inserted image on the right, where the text denotes the number of detected blobs. Let's go back to the script here. Notice that we are using a couple of system objects here, and it is good practice to release these system objects once we are done with it. So here we can say release H blob analysis and release H text inserter. Let's go ahead and run this section to release the system objects because we are done with them. The last step is to implement a loop so that we can do all these operations sequentially, frame after frame, and display the result in a video player. Importing the videos and playing them in a player has already been covered in the import video. We can just extend that example and perform the above operations in a loop. Let's open up an existing script to see how we can do that. So I'm going to go to MATLAB command prompt here and open up all frames blob.m. This script takes the buirun.avi video file, performs blob analysis on the video frames, and then annotates the video frames to visualize the results of the blob analysis. The first step is setting up, which consists of creating the necessary system objects and variables for our image processing and computer vision task here. Then we implement the loop where we do our thresholding here. So we can see the thresholding code that we are dealing with here. Then we do the morphological operations and blob analysis here. After that, we insert shape and text here, and then play the video in the video player. Remember that since we are using system objects here, we also have a cleanup section here to release all the system objects once we are done with it. Let's go ahead and execute this code to see what this looks like. You can see that the algorithm is trying to identify the green blobs here. It does a fairly good job. You can also see that the algorithm is trying to catch the farther buoys sometimes, and not just the nearest buoy. We could go back and adjust the blob area or other threshold limits to make this algorithm a little better. Let's go back to the presentation and do a recap. After thresholding, we realized there are some disturbances that need to be removed. We did that using morphological operations. There are several morphological operations to pick from, and we picked the open morphological operation. Once we judged the image is ready for blob analysis, we created the blob analysis system object and set the minimum and maximum blob areas to suitable values for us. We also used the default outputs for this variable, namely the area, the centroid, and the bounding box. Then we used step on the system object to perform blob analysis. To visualize the output of the blob analysis, we annotated the video with shapes. We took the bounding box from the blob analysis and inserted it in the video frame using the insert shape function. We then inserted text that showed how many objects have been detected in the current frame using the text inserter system object. We then talked about how to implement this in a loop for a video instead of a static image. This was similar to the video file reader example in the import video. Setting up system objects and necessary variables is the first step. Then we used a combination of functions and step on system objects to perform the computer vision algorithm. Finally, we released all the system objects in use. In summary, we did blob analysis and annotated the video to visualize the output of the blob analysis. We also saw how to perform specific computer vision tasks such as color thresholding and morphological operations. This concludes this video.